Ethylene Thiourea is a powerful accelerator, but only for chlorinated polymers. Welcome back, my rubber hearts. In today's episode, we are diving deep into the technically complex world of vulcanization with ethylene thiourea, or ETU. This molecule has long been a cornerstone in the vulcanization of certain types of rubber, specifically halogenated polymers like polychloroprene, or CR, and chlorosulfonated polyethylene, or CSM. We will explore why ETU is uniquely suited for these polymers, its role in the vulcanization process, the regulatory and safety concerns surrounding its use, and how to formulate an ETU-based rubber system correctly. Let's get started. First, let's establish what ETU actually is in the context of rubber chemistry. ETU is an accelerator, not a vulcanizing agent itself. Vulcanization, as you may know, refers to the process of forming crosslinks between polymer chains to transform raw rubber into a durable, elastic material with enhanced properties like strength, chemical resistance, and thermal stability. ETU's role as a chemical is to speed up this cross-linking process and make it more efficient. However, it is important to understand that ETU works specifically with halogenated polymers such as CR and CSM because its chemical mechanism relies on the presence of halogen atoms, specifically chlorine, in the polymer backbone. So, why does ETU only work with chlorinated polymers? The answer lies in its chemical structure and reactivity. ETU contains highly reactive thiourea groups, which interact with the chlorine atoms present in the polymer backbone during vulcanization. When the rubber compound is heated, the ETU molecules are activated and undergo a substitution reaction with the chlorine atoms. This reaction forms covalent thiourea crosslinks between polymer chains, creating a three-dimensional network. These crosslinks are incredibly strong and contribute significantly to the rubber's mechanical and thermal properties. In non-halogenated polymers such as EPDM, this reaction cannot occur because the necessary reactive sites, chlorine atoms, are absent. This makes ETU an ineffective accelerator for halogen-free rubbers, which require alternative cross-linking mechanisms such as sulfur or peroxide vulcanization. The choice of ETU as an accelerator is largely driven by its exceptional efficiency and the unique properties it imparts to vulcanized rubber. ETU provides faster and more complete cross-linking compared to other accelerators, which is particularly important for applications where precision and performance are critical. The thiourea crosslinks formed with ETU contribute to superior heat resistance, chemical stability, and aging properties, making it ideal for demanding environments. For instance, CR vulcanized with ETU is widely used in automotive applications, such as seals, hoses, and belts, due to its excellent resistance to oil, heat, and weathering. Similarly, CSM, which also benefits from ETU's rapid cross-linking, finds use in applications requiring high chemical and ozone resistance, such as industrial gaskets and protective coatings. Formulating a rubber compound with ETU requires a careful selection of additional ingredients to ensure the vulcanization process is effective and the desired properties are achieved. Magnesium oxide is a critical additive in ETU formulations. It acts as an acid acceptor, neutralizing any acidic byproducts generated during the cross-linking reaction. Without magnesium oxide, these byproducts could interfere with the reaction and compromise the final properties of the rubber. Zinc oxide is another essential ingredient, serving as an activator that enhances the efficiency of ETU and speeds up the vulcanization process. Together, zinc oxide and magnesium oxide create an optimized reaction environment for ETU to perform effectively. On the other hand, certain materials must be avoided in ETU-based formulations. Sulfur, for example, is incompatible with ETU because it interferes with the thiourea cross-linking mechanism. Sulfur-based systems rely on a different chemistry altogether and can lead to incomplete curing when combined with ETU. Acidic fillers like untreated silica are another no-go. These fillers can neutralize ETU, preventing it from forming crosslinks. If silica is needed for reinforcement, it must be surface treated to eliminate its acidic nature. Additionally, excessive plasticizers or oil, particularly polar ones, should be used with caution. These can form a physical barrier between ETU and the polymer chains, reducing the efficiency of cross-linking and resulting in weaker materials. While ETU is a highly effective accelerator, its use comes with significant safety and regulatory considerations. ETU is classified as a substance of very high concern, or SVHC, under the REACH regulation in Europe due to its toxicity and potential health risks. This classification places strict controls on its use, requiring manufacturers to comply with stringent safety protocols, including proper personal protective equipment, or PPE, and workplace ventilation. In addition to REACH, other regions have implemented their own regulations. In the United States, for instance, ETU is not banned, but is subject to occupational safety guidelines set by organizations like OSHA, which limit worker exposure to the substance. Countries such as Canada, Japan, and Australia also enforce strict safety measures, emphasizing the need for responsible handling and disposal. These regulatory concerns have led to the development of safer alternatives, including predispersed forms of ETU. Predispersed ETU typically contains 80% active ETU in a polymeric carrier, such as EVA or EPDM, which reduces dust generation and minimizes the risk of exposure. This form is easier and safer to handle, making it a preferred choice in modern manufacturing environments. To summarize, vulcanization with ETU is a highly specialized process tailored to halogenated polymers like CR and CSM. ETU's unique ability to react with chlorine atoms enables the formation of strong, heat-resistant crosslinks, making it invaluable for high-performance rubber applications. However, formulating with ETU requires precise control over the choice of ingredients, as well as strict adherence to safety and regulatory requirements. By understanding the chemistry and challenges of working with ETU, rubber technologists can harness its full potential while ensuring compliance with global standards. Thank you for joining me in this detailed exploration of vulcanization with ETU. If you found this episode insightful, don't forget to like, share, and subscribe to my Rubber Heart. Let me know in the comments if there are other topics in rubber science you'd like me to cover. Until next time, stay curious and stay bouncy.